Alright everyone, this is the last part of this chapter, which is kinetic and potential energy. After this, for this week, you just have a lab to do. We'll do a skills check quick, and then the test will be on Friday of this week, just to make everything more concise so it's not on a Monday. But the details of the test will be posted on Schoology again, like the skills check was, which a lot of you did really well. But yeah, other than that, we'll get started with kinetic and potential energy. So when we talk about the law of conservation of energy, which we've mentioned before, this also applies to any mechanical process. So when we talked about how energy must be conserved, it can't be created or destroyed, it'll apply to mechanical energy processes also. And then we're also going to talk about friction in this case because friction is also a big thing. But if friction is small enough, it will be neglected and nothing else is added. So basically, in all the examples we do, the friction coefficient is very, very small. So we won't have to worry about it, and we'll just look at the total mechanical energy. But when we look at the conservation of energy part of the mechanical energy, we're going to look at two things: kinetic and then potential energy of the beginning of the system, and then we're going to compare that to the kinetic and the potential energy of the end of the system. Okay? And that's where we talk about that conservation of energy has to be the same, where your total energies at the beginning have to equal your total energies at the end. So let's first talk about kinetic energy, and which is measured in joules, is the energy of motion. Okay? So the key part is the energy of motion, right? So it has to be in motion. It's always dependent upon the object's mass and speed. So for the equation for kinetic energy, we get kinetic energy is 1/2 mass times velocity squared. Okay, so the mass will always be in kilograms, remember? And the velocity is always going to be in meters per second like we've always been doing. So if you need to convert them into either or, you need to, but they always have to be in kilograms or meters per second squared. Now, when we talk about how these two affect your kinetic energy, if you double the mass, you'll double the kinetic energy because they're a direct relationship, right? 1 to 1. But since velocity is squared up here, if you double the speed, you actually quadruple now the whole kinetic energy. Okay? So because your velocity is squared here, if you double the speed, you're going to actually quadruple the kinetic energy. So the quickest way to increase kinetic energy, increasing speed. So let's look at an example. Okay. So we know that kinetic energy, oops, let's erase that part. There we go. Is 1/2 mass times velocity squared. So we have a 70 kilogram man is walking at a speed of 2 meters per second. What's the kinetic energy? So it's pretty straightforward one. We're just going to take kinetic energy equals 1/2 times his mass, 70 kilos, times his velocity, 2.0 meters per second, and we're going to square it. So when we do that, we'll take 0.5 times 70 times 2 squared, and then we should get 140. And remember, this is measured in joules. That's pretty much it. Really straightforward on how to use it right now. Let's look at one more real quick. Let's say we have a 50 kilogram cheetah, has a kinetic energy of 18,000 joules. How fast was he running? So let's look at our equation again. 1/2 mass times velocity squared. His kinetic energy we know when he was running was 18,000 joules. Equals 1/2. We know the mass of the cheetah is 50 kilograms. And then we're going to try and find this velocity. So we're just going to find the velocity now. So once we do all that, remember at the end we'll have to take the square root of our last number to get velocity by itself. Don't forget that. And then we'll square root it. So we should get the cheetah running at about 28 9.8 meters per second. Okay. So don't forget the end to square root the final number. So really at the end, you should be taking velocity equals the square root of about 720 to get rid of that squared. All right, let's move on. Let's talk about potential energy now. So kinetic energy was the energy related to motion. Now potential energy is the energy that is stored as a result of position and shape. So now this is stored based on its position or the shape of it. So now it's not when it's moving, basically. So potential energy is not moving. And now it depends upon the object's mass, height, and the acceleration due to gravity, because that's the only thing acting upon it now compared to when it's moving, just the acceleration due to gravity. But as soon as it starts moving, that energy, potential energy, is starting to be converted into kinetic. So as it starts moving, the kinetic energy goes down and the kinetic energy goes up. And we look at potential energy equation, we look at this guy. Potential energy equals mass times gravity times height. Again, mass is in kilograms, like we talked about. Gravity, remember we measure in meters per second squared, which if you forget the acceleration due to gravity on Earth is 9.8 meters per second. And then we'll have height in meters, right? Don't forget to have that in meters and nothing else. It has to be in meters. But again, it's going to be equal to joules in the end, so this will be equal to joules when you multiply all those together. All right, let's look at an example. So, what is the potential energy relative to the water surface of a diver at 50 kilograms at the top of a 10-meter high platform? So, it's basically saying here's the pool, here is the platform, and here's our little guy. It's saying what's his potential energy? Whoops. Potential energy here at the top before he even starts moving. So, potential energy equals mass times gravity times height. So we know his mass is 50 kilos, which is in the units we want. Gravity is just acceleration due to gravity, 9.8 meters per second squared. And then the height of the platform, which has to be in meters, which it is, 10 meters. And then we'll just multiply all those three together. So 50 times 9.8 times 10 is 4,900 joules. Okay, so there we go. Pretty straightforward with potential energy. Just take your mass times gravity times height. Just don't forget this has to be in kilograms. This has to be in meters. So when we talk about potential energy, there's also different types of potential energy compared to kinetic energy, which is just one thing. So we have what we talked about, which is the gravitational potential energy. It's the potential energy that depends upon the object's height. So this really depends upon how high it is, because then remember it has it has the same gravitational pull. So like if you were, let's say, 5 meters up compared to 10 meters up, that's dependent upon the object's height. So when you increase the object, it's raised higher due to the work it takes to climb higher. So when we talked about work is due to height and distance, so the higher you go, the more work you do, okay? And when you double the mass or the height, it doubles its gravitational potential energy, okay? Because when we talked about potential energy is equal to mass times gravity times height. So if we increase mass, we'll increase potential energy. And if we increase the height, we'll increase potential energy also, because it's dependent upon how high an object is. Okay. That's the one we just talked about. We also have elastic potential energy. Okay. This is the potential energy of an object that is stretched or compressed. And the most basic thing you guys have seen before is shocks, right? Shocks in bicycles, shocks in cars, right? That's an elastic potential energy, which is the potential energy of the object that is stretched or compressed. So when it's compressed, it's storing potential energy. When it's compressed, it's using it and it's going back and forth. And we know about these elastic springs. They spring back to its original shape after it's always stretched or compressed. So that's why they're able to store that potential energy, because they can go back to its original shape all the time. If they didn't, they wouldn't do its job of being elastic and working as a purpose as we want it to. So just a little graph looking at how I told you guys how potential energy is related to kinetic. Okay, so here's the top of it. Let's say this is like 10 meters. Okay, you're staying at 10 meters high. At this point, it's all potential energy. Okay, but as you start going down in height, let's say you start dropping, your potential energy starts decreasing and your kinetic energy starts increasing. And then you go here at the bottom portion of this, where you have no height, you're all converted into kinetic energy now. But then when you go back up the ball, it goes back up to having potential, and then at that point, when it's at its highest point, it's at all potential energy. So this just relates to how we talked about how potential energy is converted into kinetic as it drops down, and then as it hits the ground, this ball, it has no more potential energy, it's just all kinetic energy. But then when it bounces back up, its potential energy starts increasing again because the height starts to increase again, and its kinetic energy starts to decrease, and then it gets to a top off point. But remember, the energy of the total system has to be conserved. So at any time, your potential energy and your kinetic energy of the end have to equal the potential and kinetic energy of the beginning. Okay, so they're always conserved at any point.